Thanks all for coming. So we have Myra Chudnovsky from Princeton. We are very pleased to have her. And she'll talk about induced minors, treewidth.
Sure.
Please.
All right. Well, thank you very much for having me. It's fun to come here, and thank you for coming to my talk. I don't think I'm ever giving a really technical talk for such a large audience. So how that's gonna go. But I thought here I shouldn't do a survey. I should actually prove it here. But I'll start with some background. So just to remind you, 3D compositions have graph G, T, chi is a G, composition of G, T is a 3, and I is a function from the vertex of T to subsets of vertices of G, and there's some rules. Rule number 1 is every vertex of G, right? So like you should imagine a tree, it's a 3T, and then for every vertex of the tree you associate a bag of vertices of G. And there's some rules. So rule number 1 is every vertex of G is in some bag. For every G exists T such that V is in the bag defined by T. The second rule is for every edge of G, there's a bag that contains posits ends. For every edge of G exists T such that U and V are in the bag corresponding to T. And then the third rule is, if I look, so if I fix the vertex of G and I look at bags that contain it, so let's say it's here, and there. So not like this. The rule is, if I look at the vertex of G and I look at the bags that contain it, the subgraph of G induced by that should be a tree. So I'll write this down and I'll say it again. For every V to G, if I look at the bags that contain V, so it's T such that V is imply of T. That's some subset of vertices of T. And then I look at the graph that T induces on this. So this is a tree. Another way to say it, if I put V in this bag and I put V in that bag, then I have to put V in every bag that lives along the path of T from here to there. This one. Okay, so that's a 3D composition. Now, if you've never seen 3D compositions, probably this is not very illuminating, but on the other hand, I'm not going to use this much. If this is a topic of my talk, I need to say this. So now, okay, so here's, I give you a graph. Here's one 3D composition you can make. Take one vertex tree and put V of G in this one bag. That's definitely a 3D composition, but somehow that's not a good representation of G. So you want to measure the quality of your 3D compositions. So let me say the width of a 3D composition is the maximum size of the bag. And then, so what I just did was a really bad 3D composition. It was a 3D composition of huge width. What you want are good 3D compositions, meaning 3D composition of small width. So the treewidth of G is the minimum over all 3D compositions of the widths of the 3D composition. Okay, and this theory of the graphs with small treewidths, in some sense they're trees, you can design efficient algorithms for them. Let me not talk about it, but let's kind of agree that we like graphs of small treewidths and we want to know what they are. Now,
maybe you want to add one somewhere?
yes. So, minus one. Minus
I like plus one.
Yeah, exactly.
I
think we're
minus
like 100.
yeah.
Yes. Okay. So, So let me just define one more notion. So for some reason, it's interesting to think about tree decomposition, except I'm not allowing you to use all trees. I'm only allowing you to use path, and that's called path width. So path width of G is the minimum over all T pi, where T is a path of the widths. How about I put my minus one
Yeah, sure.
where everything fits. So this is something people think about, treewidth, path width. I mean, I think you can kind of think about things in between. What if I give you a tree that doesn't branch too much? What's the best width for trees like that? That's an interesting concept also, but I'm not going to talk about it. Okay, so treewidth and path width, people have been thinking about them. They're all both nice concepts. And what we want is to understand which graphs have small treewidth and which graphs have small path width. Now this is not about defined questions, which graphs have small treewidth. Graphs have small treewidth. But so let's ask a better question: what do I need to exclude to guarantee small treewidth? And what do I need to exclude to guarantee small path width? So this is a slightly better defined question, because what do you mean exclude? And what containment relations? And there's some containment relations it's known, and there are others it's not. It's not about that. So characterizing by excluded minors. And there are two, so that's known. There's a theorem of Robinson and Seymour from 1996 that says for every t there exists c such that if g is wtt minor free, then treewidth of g is equal to c, and WTT, so you probably, everybody knows the T by T grid. That's this. So this is G to T, but for reasons that will become clear in a minute, I want to think about the T by T wall, and the best way I know how to describe it is you start with a grid and you erase every second vertical line. So you erase this and that, and that. And now here I'm going to do it that way. Erase this, and this, that. Here I'm going to do it the first way. This, and that. This one. This, and that. And so this is the wall. It's made of bricks. The reason I do it this way is because, so I call this, like I started with a T by T grid. Now this is a T by T wall. If I didn't start with a grid, it's not completely clear what T measures. But it's not very important because everything will be qualitative anyway. Okay, so this is that theorem. And then there's a parallel theorem for path width. So also Robertson and Seymour 3 years earlier. For every t there exists c, so that g is bt minor free, then treewidth of g, path width of g most c, and here bt is a binary tree of height t. So this is b1, this is b2. Okay, so that's minors. Now, the nice thing is, from this, very easily you get a theorem for subgraphs. And all we need to say is subdivided wall subgraph, and here subdivided binary tree subgraph. Now we get two theorems with pressure. So to go from the white theorem to the purple theorem is easy, because if you have a cubic graph, then containing it in a subgraph containing with the minor is the same as containing with the subdivision. And so. Okay, so that's all known. That's all very beautiful. But now, what if I want to be in the induced world? I think it's best to introduce. Oh, I see. It does.
Okay.
So what about induced obstructions? Oh, so one thing I should say, this is best possible because this has large treewidths and that has large passwords. So if I don't exclude any wall, then I'm going to have a class with large treewidths. If I don't exclude any tree, then I'm going to have a class with large passwords. So somehow this is best possible terms we can come up with. Okay, so what about induced obstructions? And here I want to think about induced subgraphs. I know what that is. And induced minors. And just tell me what an induced minor is. So you know what a minor is, right? H is a minor of G. Let's say the vertex set of H is H1 through HK. And then it is a minor of G if there exists pairwise disjoint connected connected subsets of V of G such that if HI HJ is an H of H, then there is an H in G from n side to extreme, right? You probably know this definition. This is H. To contain H as a minor means you can find 4 connected subsets. And there's an H here, and here, and here, and here. So that's minor. What about induced minor? Well, it's almost the same. Right, so minor to subgraph is what induced minor is to, no, sorry. Induced subgraph to subgraph is what induced minor is to minor. So you want that to be H is if and only if there's an H in the thing you're trying to contain. So H is induced minor of G. If there are pairwise disjoint connected subsets, one for every vertex of H, and now this is if and only if. So, if this and this is if and only. I'm not sure sentence. So if two things here, these two are non-adjacent, so I'm not allowed to have any edges between x1 and x3. So these are the two containment relations I'll be talking about from now on. Minors was from historical perspective, mostly. Okay, so now let's think about what kind of analogs of these two theorems you can get if you're interested in induced containment relations. Okay, so we have treewidths and passwidths. So for treewidths, you have to exclude WTT. Oh, actually, so for both of them, for both of them, you have to exclude big cliques. Right? The big clique has big treewidths, and therefore big passwidths. You have to exclude big complete backtrack graphs. And then, so for treewidths, so for treewidths, you need to exclude wall-induced minors. For passwidths, you need to exclude binary tree-induced minors. Now, what about And you have to, right? Because these have big treewidths and these have big paths. What if I wanted induced subgraphs and not induced minors? Well, it turns out it's not much harder. Here you need to exclude subdivision of wall and line graphs of the subdivision of wall. And here you need to exclude subdivisions of the tree and line graphs of the subdivision of the tree. And so excluding these as an induced minor, those as induced subgraphs, turns out to be the same. And similarly here, doing this as induced minors, those as induced subgraphs, turns out to be the same. Okay, so
BT over there, right? Yeah.
was
Is
it?
that-
Yes, yes, yes. Now here I want to say induced. So this is a little bit question. So here I definitely need to exclude this as an induced minor, and you can write it in terms of induced subgraphs. In theorems it says if you have this is induced minor, then you have 1, 2, 3, 4 as induced subgraphs. But it's not a nice theorem like this. It's ugly things. And for this, for now let me say something. Induced subgraph, which is the same as subgraph. But I'll come back to this in a minute. Okay. So this is what we have to do. Now, it turns out with passwords, everything works very nicely. Here, where t exists c such that g is kt, ktt induced subgraph free, kt subgraph free. For kt, it doesn't matter if it's induced or not. KTT induced minor free, and BT induced minor free, then passwords of G is the most, and that's a theorem with several attributes and so much more. So like I said, if I wanted to, in a minor, an induced subgraph theorem, I could. So for this, we know how to translate it to induced subgraphs. For this, really, all that's missing is some graphs of the form. You take many pairwise anti-complete paths and stable set of vertices, and each vertex has a neighbor in each path, and then you can give some more rules about what this looks like. But it's some graphs of this kind. There's a theorem about that. Okay, so that's very nice.
There's a eraser, yes.
So passwords we completely understand in the induced world. What about treewidth? Well, with treewidth it's not good. Because there are lots of constructions that show that excluding what I wrote here is not enough. Constructions. Treewidths and without all those things. Just write this again. KT. Subgraph, KTT, and TT. Okay. So, actually, I said lots of constructions. There are lots of constructions if you say this, and there are lots of constructions. If you say this, then there are few constructions, but they still exist. What I wrote is correct. That's in Induced minor, yes. Okay, so now there's something a little weird about this, right? This is an induced minor, this is an induced minor, this is a subgroup. So what if I try to say induced minor? Well, then it's true. And actually, if I say this, I don't need to say that, because if I contain this as an induced minor, I contain that as an induced minor.
Yeah.
Right, so we're now doing an alternative theorem, we're doing a purple theorem. And so that's the purple theorem is a result of so let me not write it here because it's starting to be false. So theorem of Volcker under Kim colleague Setieri and Trotignon. It says for every t exists C such that G is KT and WTT induced minor free, then treewidth of G must C. Now, this is lovely, except excluding this as an induced minor also means you exclude it as a minor. Like induced minors is all about respecting non-edges. If there are no non-edges, there's nothing to respect. And then all the very strong tools from graph minor theory kick in. And so it's nice, but somehow it's not really a theorem about induced subgraphs. It's a very strong theorem about minors, and then you can reduce some. Okay. So even though this theorem exists, in this talk, I'll always be in this. Exclude KT as just so that I can't use the graph minor theory quite so much. Okay. Next. All right, so now we've agreed on what we need to figure out. So we're done with this. We're done with pathways. We're thinking about treewidths. We want some kind of an induced characterization of bounded treewidths. That's what's left. Characterize classes of bounded treewidths by induced minor subgraph, where we know that we forbid KT subgraph, KT induced minor, and WTT induced minor, and as I already said, if you prefer induced subgraphs, you can restate this in terms of induced subgraphs. Okay, so need to. So now, what you want is to say if you have something of large treewidths and it doesn't contain any of those things, then there's some other thing of large treewidth that it contains as an inducement or as an induced. Let's say induced subgraph as an inducement. Right, and you have to say some other thing of large treewidth, otherwise it's treewidth, like contains an edge. That's not the theory we're looking for. So, but it turns out there's no theorem like that. It's a theorem of Alecu, Bonnet, Trotignon, and Villafana that there's no theorem like that. So now let me say what I mean. So what? Class H such that if G has large treewidths, huge treewidths, then G contains H and H of large treewidths. Right, so somehow this H is a witness that G cannot be too trivial from the point of view of treewidths. Maybe H does not have huge treewidths, but has large treewidths. And because this is a hereditary world, let me say hereditary. Okay, so what they proved is that the only class H that works is the class of all graphs. Alecu, Bonnet, Trotignon, and Villafana. If H is as above, then H is the class of all graphs. Right, so somehow you shouldn't try to prove something like this because there's no interesting H with this property.
Here, what does contains mean?
Yeah.
Yes, excellent question. As induced. Okay, so this is kind of, one might argue, the end of this investigation in the world of induced subgraphs. I mean, the only thing you can negotiate is where this heredity came from. If you don't say that, then this is not good. But on the other hand, if you don't say that, that's probably not going to be good. Now, for induced minors, the situation is not good either. I don't want to explain it because it will take me the rest of my talk. But somehow trying to prove a theorem like this, saying induced minor here is probably not a great idea. So then let's do something else. Well, one interesting thing is that in all these known constructions, while the treewidth is unbounded, it doesn't grow very fast as a function of the number of vertices. So in all these known constructions, actually treewidth is logarithmic in the number of vertices. Constructions. Treewidth is about log the number of vertices. Okay, so now it's a conjecture that I suspect is probably true, that under these circumstances, treewidth is in fact, I don't swear that it's logarithmic, but poly-logarithmic. Conjecture. Wherever t is c, such that if g is kt free, w kt is subgraph free, w tt a tt is minor free, then treewidth of G most the number of vertices to this. Now, I think if I think hard enough about it, I can convince myself, and even you, that you also have to put a C here. because otherwise it's false for graphs with 0 bits. So it's 1 bit. Something. I don't know whose conjecture this is. It may be mine. Maybe not mine. I don't know whose conjecture this is. The world suggests that this is true. If anybody here thinks it's their conjecture, they should definitely claim it. If somebody here honestly thinks it's their conjecture. Okay, so this is open. But what I want to show you is some parts of a proof of a weaker statement. So let me see. So the idea here is treewidth grows slowly as a function of the number of vertices, and it grows so slowly that something interesting happens in the world of algorithms. So let's say our benchmark problem is max weight independent set, but there are many others that are equivalent. So if treewidth is logarithmic, you can solve max weight independent set in polynomial time. If treewidth is poly-logarithmic, you can solve max weight independent set in quasi-polynomial time. And what I'm going to show you is a weakening of that still allows you to solve max weight independent set in sub-exponential time, which is already something. So students Julian Kotze and my other students David Fisher and Tanya Roshnet. For every t that exists C, such that under the same assumptions, G is AT, W, AT subgraph free, WTT, ATT, induced minor free. Then the treewidth of G is subpolynomial. It's more than log n to the epsilon to an epsilon. So treewidth of G is at most, we call this C epsilon, is at most this 2 to the log n to the 1 minus epsilon. Okay, so Givers. So right, 2 to the log n is n, just to practice. 2 to the log n is n. 2 to the square root log n is subpolynomial, and this is still subpolynomial. So now I just learned about these numbers last fall, so but I'm told that this is smaller than log n to the delta, than n to the delta for everything in some asymptotic sense. And also I'm told that this implies some exponential maximum independence. Okay. I mean, it's so it's subpolynomial. It's better than any polynomial. I mean, there's some asymptotics here. N is very small, then it's not true.
You mean it's better than any linear term?
Here delta is small. Delta is less than.
Yeah, it's better. It's sublinear.
No. It's better than this, and it's better than that.
Yeah, so it's better than any sublinear.
Yeah.
Yeah.
Oh, sublinear in that sense.
Yeah. I mean, it's more than subpolynomial. Like it's even sublinear.
Well, it depends if you call this polynomial.
No, it is polynomial, but it's also sublinear.
But being smaller than n to the 1/2 is better than being smaller than n. So what I'm saying is stronger than what you're saying.
Yeah, so it's better.
I'm scared to argue with you because you thought about this more than I have.
Yeah.
I think I get what.
Okay,
okay. So not only is it smaller than n, it's even smaller than square root.
Into the 1/100 or whatever.
Yeah.
Anything.
Oh, that you're gonna take a picture of. Okay, so the good news is that I wasted enough time. Going into the details of the proof, but I'll try to do some of the proof. So, the one important insight, which I will not prove, but that's an insight of Robertson and Seymour, is that in order to prove that something has bounded treewidths, it's enough to prove that there are small balance separators. You can delete a few vertices and the graph breaks up into roughly equal parts. Now this is a much easier thing to think about than treewidths, right? So, okay, so that's a good step number one. Then good step number two, which is something that I'll explain here, is actually it's enough to think about separating a pair of vertices. It's enough to think about, under some circumstances, which are relevant for us here, all you need to do is separate pairs of vertices by small sets. That's an even easier thing to think about. That's really just two vertices. So that's kind of a good double simplification, and we use it. We use it in proof. But let me get there. Proof sketch. So step number one is not ours. It's a theorem of Bonnet. Poly-logarithmic and sorry that. So now I'm always assuming G is in this class. I'm going to say G has this and G has that, but what I mean is under these circumstances. And also I'm going to be a lot less precise. G has a coloring, proper coloring, C1 to C and T, such that for every I and J, the graph induced by G on Ci union Cj is a star first. So what's a star forest? It's a forest where every component is a star or an isolated vertex, isolated vertex. And that tells you that the H set of G is the union of sets Eij. Such that Eij looks like this. It's just a bunch of stars. And not only that, it looks like this, but also this is actually induced. Right? So Eij looks like this, and also it's induced. And I want to say this a little more, even a little more restrictively. So here Ij is an order, meaning the stars have their centers in Ci and their leaves in Cj, and the isolated vertex. So this is the kind of star forest. All centers are in Ci, all leaves are in Cj. There's some more isolated vertices in Ci, and then all others.
No, you mean you can assume that, or you can just you introduce more colors to do that?
so if you started with this, so you had some stars that looked like this, and some stars that looked like that, and now some isolate vertices here, and some isolate vertices there. So, and now you can say, you introduce more colors here. EIJ is not the same as EGI. So it's a trivial observation, but it's a convenient way to do it. Okay? So EIJ is this, and EGI is that. If I want to think about the star forest, this is the purple one, this is the green one. Okay, so now the trick is you define the complexity of your graph, or the dimension of your graph, as follows. You ask, in how many EIJs do you have large degree? And I think large means 3, but let me say 100 to be safe. So the dimension of G is the number of ordered pairs IJ such that the graph with vertex set, V of G, and edge set EIJ has max degree. Right, at least 100. So okay, that's the dimension of the graph, and now the whole proof is by induction this dimension. And when the dimension of G is 0, meaning it's your degree, so if the dimension of G is 0, then max degree is 100 times f of t. Max degree is gone. Then it's true. In fact, treewidth of G is at most some t of t, and that's it. Okay, so at least we have our inductive stuff. So now, okay, so now I can assume my dimension is something, and I'll try to reduce it to dimension 1 small. So let me take step 2. Let me look at some EIJ as big degree. At least there. So remember, it's a bunch of stars, so it's subset Ci and Cj, and the graph induced by the observations. Okay, so let me contract all these stars. I'm still in my class because contraction is okay for induced minors. You need to be a little bit careful for not increasing the click number, but you're okay because it's a very special thing to contract. And now you ask, is the treewidth big or small? If the treewidth is big, you win immediately. Because if the treewidth is big, then you contain, just by the Robertson theorem, a large wall. Now, some vertices of this wall are these contracted vertices, and some vertices of this wall are real vertices of the graph. So now uncontract, right? If this was a contracted vertex, replace it by, let's say, this vertex came from that star, so replace it by this and this and that. And you can do the same thing for degree 3. And what you got is, after you did this uncontraction, is still a large wall, but now the degree in the EIJ is only 3. So you have a big treewidth graph of small dimension, of smaller dimension. So if you're proving that doesn't happen, you're done. So you can assume when you contract, treewidth goes down. And not only that, what I just did, I can delete any number of these and contract all the others. And by exactly the same argument, still treewidth goes down. So that's very strong. My one big difficult graph is lots of subgraphs where if I contract something, treewidth goes down. And that means, so however I delete a subset of this, there's a tree decomposition where every bag contains a few of these stars and a few vertices. So it's not a bounded width tree decomposition, but it's a tree decomposition where every bag consists of a few IJ stars, a few stars that look exactly like this, plus a few vertices. Okay, so that's a good step.
Can you repeat the argument again? So when you have EIJ with big degree and
So you
then
contract the stars,
contract one star,
all stars,
all stars.
all stars.
Uh-huh.
And now you ask, is the treewidth bigger or is the treewidth small?
Uh-huh.
And I claim the treewidth is small. Now, what is small? It's something to do with the bound you have for the previous dimension.
Uh-huh.
It's a little bigger than the bound you have for the previous dimension. Specifically, it's the bound you have for the previous dimension. It doesn't matter. Because suppose not. Suppose it's bigger than the bound you have for the previous dimension. It doesn't matter. Then, in this contracted graph, you have a subgraph that looks like this, of size the width for the previous dimension. So now you do this uncontraction. And when you do that uncontraction, the degree you introduced in the EIJ is at most 3. Because all you need from this vertex is to preserve this neighbor and that.
Because these subgraphs there.
Yeah, because the subgraph looks exactly like this. And then, so now you have something of dimension of treewidths, which is too big for dimension 1 smaller, and yet you reduce the degree in the EIJ. That's a contradiction, because that's a graph of smaller dimension. And that's why in fact the handle is 3. Okay, so the treewidth is small. And so what I just did, you didn't have to contract all this stuff. You can delete some centers and then contract the rest. It's exactly the same. So do for every C subset of CK, G minus C has a tree decomposition where T chi such that for every T of T is few stars, A stars plus A EIG stars plus B vertices, and A plus B is at most 2 to the log n to epsilon minus omega. That's interesting. Except the epsilon dimension much smaller, except in intermediate. Big number. Okay. So that's good news. Now, okay, so now we're going to reduce it to separating vertices. So what I'll do now is, so I have this G decomposition, right? So let me start with C equals empty. G has a G decomposition like that. So I can pull out a bag, and that's a balanced separator. Right? So I can pull out a bag that looks like this. And this is small. This is, let me, small. And I call this number R. But R is that. Okay, so let me delete from the graph this set. And now I claim again I have a tree decomposition at the same time. So let me pull out another balance separator. And let me delete this part. That's another. And we're going to do this a bunch of times. I'm going to do this sub-polynomial many times. So eventually, I have something with G minus small set. And on the side, I have all this, I call them cores of my valid subgraphs. And there are quite a few. P of them I'll tell you maybe what P's. I'll finish by.
You have 10 minutes.
Oh, I have 10 minutes.
Yeah.
I'll definitely finish. Okay, so now step 3 is G is PQ slim. And this P is that big, so then you tell me what PQ slim is. So PQ slim means out of P vertices, out of every P vertices, there's one pair that are not ends of a Q wide theta. So there's one pair so that between them you can't find Q pairwise complete class. For every P1 P exists Pi and Pj such that there do not exist Q pairwise anticomplete internal. Give you lots of vertices, then there's one pair which is poor in some sense. It doesn't have Q paths, Q anticomplete paths.
What is incomplete paths means?
Anticomplete means no edges between. Disjoint and no edges.
Oh, okay. Induced.
Okay, so making progress. I give you lots of vertices, namely P, then there's one pair where I cannot find this of width Q. Okay. So now I claim, if only I could separate every Q slim, every, so this is called Q slim. So a graph is PQ slim and a pair is Q slim. So now I claim, if only I could separate all Q slim pairs by small separators, I'd be done. Step 4, which I won't show you, prove that every Q slim pair can be separated by small separators. So let me not prove that, but let's say prove that. So now let me show you why this and that together is equal. So remember, by step 3, I generated some subgraph of G that I don't know anything about, and a bunch of specific P sets, each of which is not very big. And so that for each of which, if I take vertices here plus their neighbors, that's balanced. Okay, so now, so let me call this R1 through R. So now let me add, so now for every Q slim pair here, let me add a separator for that pair, which I know I can do. So that is R1 through RP together with X UV or UV R1 to RP and UV is Q. So that's still not a very large set if you're in the sub.
The size of our line could be 8, right?
Subpolynomial, because it's the treewidth of the previous dimension.
I see.
Right, so this is subpolynomial, but smaller than 1 for now. This is subpolynomial squared, which is still subpolynomial smaller than 1 for now, plus those which are also subpolynomial. I can draw. So now claim Z is a balanced separator. And if only I could prove that, then I'd be done. Because we already said balanced separators is the same as trees. Small balanced separators is the same as trees. So why is that? Well, suppose here is a big component of Q minus. Now remember, when I removed Ri plus their neighbors, there were no big components. Because for each I, Ri plus its neighbors was a balanced separator. So that means for each of these Ri's, some guy there has a neighbor in this component. Okay? Because this is not in the neighborhood of R1, this is not in the neighborhood of R2. So there's R1 in R1 as a neighbor here, and R2 in R2 as a neighbor here, and RP in RP as a neighbor here. But then there's a pass, but then it's pivots. Some pair is Q slim. So there shouldn't be a path left between them, but there is one. That's it. That's Z modulus tech 4, which I'm going to do. Okay, thank you.
Thank you. Any questions?
Yes.
Sorry.
If I want obstructions for tree alpha, like, do you think it's
I think it's the same conjecture. It's poly-logarithmic if you exclude WDT and KTT. So I can maybe tell you that we are writing a version of this for tree alpha.
Tree alpha.
I see.
Hopefully it will
So
soon be true.
do you have any lower bound or like what is the, and you have this upper bound, but any instances where?
Log is a constant. I would love a log square. I would even, here's a problem I really want to see solved, but I really don't know where to start. So we have a theorem that if you exclude all three path configurations, that's two vertices and three pairwise and complete paths between them, and two cliques and three pairwise and complete paths between them, and a vertex and a clique and three pairwise and complete paths between them. So exclude all of those. Then we can prove that tree width is log n squared. But the best construction we have is log n. So prove it's at least log n to the 1 plus epsilon. Ideally prove it's at least log n squared. At least prove it's at least log n to the 1 plus epsilon. I don't know where to start thinking about this. I have no idea. Whereas, and the reason it's interesting is because there's a kind of a qualitative difference between log n and log n squared. It's going from polynomial algorithms to quasi-polynomial.
I guess you also get the algorithm to find such a 3D composition.
Yeah.
Going for the application. Yeah. Like just
But that's you.
yeah. Just polynomial have. Stuff. Any other questions?
Everything else was completely clear. This was the only point that was not completely clear.
Yeah. So if not, let's thank the speaker.